Thank you, Dr. Yana. Um, a few years ago, I presented the first sketch of this work in Oxford, so it's rather suitable to present the final version, let's say, of what I've been working on. And it regards presenting domestic cats as poisonous animals. As you already know, the venomous mammals are a few and famous. Poisonous mammals are even rarer, as we can say. There are some cases of human poisoning by eating the liver of some sea mammals, but the most famous poisonous mammal is the African crested rat that incorporates plant toxins in their hair and becomes itself a poisonous mammal. But for this presentation, I'm going to focus on the relationship between the domestic cat and the different species of venomous slow lorises. The slow loris is a prosimian that has a modified gland which the animal licks and loads modified teeth to be used as syringes or needles to inject this toxin into prey and possibly predator. But as we will see, humans are especially prone to anaphylactic reactions when bitten by loris. There is a strong evidence for this toxin or secretion working as a deterrent for olfactory-oriented predators, also to eliminate or reduce the parasite load of some invertebrate parasites, arthropod parasites, sorry, but also in intraspecific competition, in which we can see from this picture, the toxin causes hair loss, blindness, and commonly death. It is known that the main component of the slow loris venom is called brachial gland exudate protein, or BGE. It's able to load various hydrophobic components that it obtains from diet. So this protein acts as a box or a snare, entrapping these hydrophobic molecules. And since 2002, we know that this main component is similar to the FeLD1 cat allergen, or the main domestic cat allergen. So the logic was that loris venom causes these effects on humans, as has been portrayed in the literature since the 70s, because it's similar to a cat allergen. So it's like an overblown allergy. It's not a true venom. And I began to think about it the other way around. What if cat allergies are in fact intoxications? And so last year, with the publication by Scheib and co-workers of one of the slow lorises, Nycticebus javanicus, full sequence for the BG protein, confirming its similarity to FeLD1, this main cat allergen, I could proceed with a more in-depth sequence analysis. So FeLD1 is the name of this major cat allergen. Cats are present in at least half of the households in the world, and about 10 to 15% of adults are considered to be sensitized to cats. And as we proceed to globally adopt an westernized lifestyle, cats become more and more present as pets, so increase the load of indoor allergens. And despite the most common effects of this allergen being the asthma and some sorts of conjunctivitis, there are cases with fatal complications. In cats, FeLD1 is produced in glands, the salivary glands, sebaceous glands in the chin area, and also anal glands, and it's spread and deposited in the fur and skin through licking. FeLD1 is a highly glycosylated protein. The glycosylation structure in volume is almost equivalent to the protein itself when hydrated. And this glycosylation is variable. So here I show the largest glycosylation tree identified so far in FeLD1. And the shaded boxes are placed on monosaccharides that may or may not be present depending on the analysis. So we have at least 5 different variant glycoforms of FeLD1, but based on other glycoproteins, we most likely have a lot more than that. It is also known that FeLD1 is able to bind different lipidic hormones and other hydrophobic molecules. The protein has this structure of a dimer of dimers. So 2 identical structures able to each hold in their central cavity one large hypophilic molecule or compound. The presence of the protein has been confirmed for some wild cats, big and small, ever since the 90s. But only recently the genome sequencing was available for a lot of them. So using the slow loris sequence for BGE and the domestic cat sequence for FeLD1, I did some genome mining and identified the equivalent sequences in 28 species. And this sequence alignment is different from what we normally see. Here, the bright colors indicate difference from the majority rule. So we can see that it's a highly conserved protein, with the exception of the light shaded boxes that are conserved positions regarding cysteine residues. And here for the second chain of the protein, we can see that it's less conserved, but still having the essential residues, let's say, the cysteine residues, the glycosylation position, and the hydrophobic interaction regions somewhat conserved. It is clearer to see, I think, in this structural representation in which blue is the highest conservation. So we can see that the interface region is the less conserved of the residue positions in the amino acids. They are present in the chain 2, while the cavity that's mainly formed by chain 1 is more conserved in all species analyzed, either loris or cats, wild or domestic. And the schematics in blue and yellow represents the dimer of dimer with chain 1 and chain 2 forming, we can say, a sandwich, or that box that faces a similar or identical dimer, but not in a symmetrical face-to-face way. We can see from phylogenetic inspections that Felis catus, or the domestic cat, FeLD1 is the most similar sequence to the slow loris sequences identified for chain 1, but not for chain 2. And in general, chain 1 respects the overall clustering of Felis species separation as recognized today, and somewhat less for chain 2. And this might indicate that chain 1 is the one responsible for the effects we are seeing both in slow lorises and in domestic cats. And I keep saying domestic cats because my hypothesis is based on allergy. That's normally considered an overblown response from the organism to an external antigen. But ever since the Profit proposition that allergy is our endogenous defense against toxins, this has become more and more confirmed.
Oh my God.
So sneezing and vomiting, scratching, and diarrhea are considered defenses of the organism towards these antigens that are external and probably dangerous. So it has been seen that we can immunize model rodents with different animal venoms, different animal toxins, and they have a response based on IgE, like an allergy, and not an IgG response. And also different arthropods that are venomous, also wrinkles and Crotalini vipers, cause allergies in people that are independent of the injection of their venoms. They are able to cause allergies by contact, external contact or mucosal contact with their toxins. So this is an evidence that venoms can be poisons and act inducing allergies. Furthermore, these proteins are secretoglobulins. They are restricted to mammals. Normally, allergens are widespread and related to parasites, so that should not be the case. They are disulfide rich, which is a structural feature that's commonly seen in venoms associated with physical resistance and environmental persistence. For instance, the island of Tristan da Cunha, which eliminated cats more than 40 years ago, still detects FeLD1 in the environment. They are intact folded proteins, also in the Iceland ice shaft. This protein can bind multiple hydrophobic ligands, such as hormones and fatty acids, as I said. It's related to intraspecific communication. Cats show relations to sex and behavior related to the levels of this protein. So males in general have more FeLD1 than females. Handling avoidant males have more than social males. And handling avoidant females have less than sociable females. And there's a very interesting study developing on how the female behavior of the domestic cats is so much more complex than other cats, and that they are under constant stress when they have kittens. Also, rodents are able to eavesdrop on feline odor signs through the pheromone hypothesis. So rodents identify signals from cats, and cats may identify signals from rodents. There are some theoretical studies combining androgen binding proteins from rodents and FeLD1 from cats, and they are so similar that they could bind, but there's no evidence that happens in vivo. There are no evidence for allergy regarding any other cat except the domestic cat, and we should expect some report on allergy to other cats, considering that, for instance, tigers are much more abundant in captivity as pets than in nature, and also in zoos, but we have no reports on that, while lorises that are rare, nocturnal, and very shy have multiple reports in the literature regarding intoxication. So my main hypothesis is that cats, different than dogs, have domesticated themselves, and this is the main driving force towards the maintenance of this toxicity-inducing or allergy-inducing protein. FeLD1, the gene, is not under selection. However, domestic cats have a large array of olfaction-related genes, especially chemiosensor genes under positive selection that are not under selection in other cats. And the major difference in this case is that the conformational variation induced by glycosylation and ligand binding may be the driving force towards the difference toxicity observed for cats, including differences in the same individual. There are multiple reports of people that are not allergic to cats and from one day to the other become allergic to the very same cat they always had. So this conformational variation may be associated with that. So as you can see, domestic cats use FeLD1 for multiple functions, including inter and interspecific communication in the case of prey detection avoidance, and also human deterrence. That's the new, let's say, aspect of this protein. And this puts FeLD1 in equivalence to BG protein from slow lorises as a moonlighting toxin. There's still much to be done regarding biochemical research with the multiple glycoforms of FeLD1, the multiple ligand interactions that have been only observed computationally, and also in interspecific monomer interactions that are not confirmed in vivo. And there are being proposed FeLD1 reduced or no cats using different techniques. We know that FeLD1 no cats are not viable, so FeLD1 does something essential for the embryo survival, but CRISPR-Cas9 techniques are being used to delete FeLD1 in the salivary glands. And the question I posit is, what will we be losing if we do not fully understand what this protein is doing? If all domestic cats eventually become FeLD1 free, or at least tissue specifically FeLD1 free, what can we not know about this putative toxin? And also there's very little information on the usefulness of FeLD1 to the cat. For instance, we know they are not viable without FeLD1, but why is that? It's not because they cannot lick it and use it to communicate with other cats. There's some more basic principle behind that that we still do not understand. I'd like to thank Eduardo Eisrich from the IUCN Cat Specialist Group that helped me with some cat genomes, and Professor Anna Nekaris for the invitation and many insightful discussions over the years. Thank you very much.